the day, and I guess in total this is 7th lecture on the topic of nanotechnology and climate change. Or you need something?
No.
Okay.
Okay.
Yes.
Sure. Thank you. Okay. Oh, no signal.
होगा सर इसका आना फ्री है
Yeah.
Okay. Okay, welcome back. We are making a big switch from bacteria, from viruses, from biology, and we will talk now for 2 lectures on a very big subject, huge subject, which is called energy. Now, this is such a big subject that we cannot cover everything. Nanotechnology has many applications for the energy world. We cannot really talk about everything, but what I hope to do will give you some ideas what nanotechnology can contribute, how it can help our energy applications, particularly alternative energies, both solar energy, which is very important if we want to survive in this world, and also energy storage, batteries, for example, which is also very important for the energy applications. So this lecture we will discuss 2 things. The first subject will be talking about conductive nanowires. We need to talk about conductivity because anything with energy has to go with electricity. And electricity requires conductivity. So we're going to talk about conductive nanowires. Then we will talk about solar cells. Again, solar cells is a huge field. We're going to talk about 3 different subsections in the solar cell field, which is dye-sensitized solar cells, semiconductor quantum dots in solar cells, and some discussion of green solar cells. Now, nanowires. Why do we want nanowires? We're all talking about smaller and smaller computer. We all want our cell phones to have more and more data. We want to have computers that can give us beautiful pictures and videos and movies and whatever. All these things need electricity. All these things need to carry electrons from one place to another place. That's how electronics work. So we definitely need small things, small features. And if we have nanowires, this will be very good as parts of electronic circuits. Very small electronic circuits. This is just an example of making metal nanowires. Now, why do we want metal? Because they are conductive, okay? There are many ways to make metal nanowires. Here, this is just one example of making metal nanowires. We start with ions, which we reduce. Then they nucleate and make seeds. And then we can take the seeds and attachment together side by side until they make metal nanowires. There's other techniques to make metal nanowires. Overall, you can see we end up with a long wire. All these things here, these dots, are single atoms of metals. Now, as I said, we definitely need those metal nanowires in electrical miniaturization to make small and small electronic circuits. See, this is just an image of a circuit that you can find, for example, in your computer. You see here, all these are wires. So if you want to make something small, we need small wires. We need these wires to be nanowires. So metal nanowire technology is critical for the new world of microelectronics and nanoelectronics. For example, our cell phone. If you look at the screen of our cell phone, the screen of our cell phone is actually conductive and it's also transparent. It is one of the technologies that people use in the screens of cell phone is made of silver nanowires. Now, because they are nanowires, they allow electricity to go through. Because they are so thin, they don't block the light. And that's why we can see the screen very easily. So just a beautiful example for nanotechnology, nanowires in electronics. Another reason we like nanowires and we need to use nanowires is the issue of heat dissipation. You know, heat in electronic circuits is a big problem. When you have small wires and you have electricity going through, the wires get hot. That's a natural phenomenon. Electrons also generate heat. Now, if we have a very small circuit with many wires and they're all getting hot, it can burn the circuit. It can burn our computer. It can burn the small electronic components. This is really a big problem in electronics. Now, if we make and if we use nanowires, we minimize this problem of heating because the nanowires are so small and there's a little amount of heat generated and we're in good shape. So these are very good reasons, very important reasons that nanowire technology is very important to microelectronics and nanoelectronics. And all the electronics companies, Samsung, Apple, all these companies are investing billions of dollars to make small nanowires that will be conductive, not generating heat, and take very little space. Let's switch subjects and talk about nanotechnology and solar cells. So as I said before, this is a huge, huge field. Lots of different technologies, different developments. Okay? And I'm going to give you very few examples of the relationship between nanotechnology and solar cell technology. Now, what do we need in solar cells? The basic concept of solar cell is very simple. We take light, we shine light, and what we want when we shine light, we want to generate electrons that will go from one electrode to another electrode. That's all what we need in solar cells. Shining light, and when you shine light, you have electrons. When you have electrons, you have electricity. Now, even if this sounds so simple, the actual thing, how to get electrons when you shine light, this can be quite complicated. And there are many technologies to do this. Shine light, generate electrons. And what I'll tell you is how nanotechnology can help this process of shining light and generating electrons. Now, some of the concept here might be a little complicated. Don't worry if you don't understand. But if you just understand the reason why we want nanotechnology in solar cells, by itself, this is going to be okay. So this is the basic concept of a solar cell. We have one electrode. We have another electrode. Usually, the sun comes from one electrode, so this electrode usually needs to be transparent. Okay? The bottom electrode does not need to be transparent, but all these electrodes, they need to be, or particularly both these electrodes need to be conductive. Okay? Now, one of the most important parts of the solar cell is here. This is called the emitter. The emitter is a material that when you shine light, it emits electrons. Now, it sounds very simple and very easy. It's not so easy. And what nanotechnology can help us is designing emitters that will be very efficient and very good and very stable. Because this is the secret of solar cell technology. If you have good emitters, you have good solar cells. If you have emitters which are not so efficient, the solar cell that you make is not going to be so good for generating electricity. Now, the emitter generates electrons. This is an electron. Now, when the emitter generates electron, it's also generating a hole. The electron is negative. When it goes out of the emitter, you have a hole left behind, a positive hole. The problem with solar cells is that the electron combines with the hole and does not get to this electron. What we want in a good solar cell is electron generating in the emitter. It will go all the way to the other electron, and then it will go back. And when the electron will go back, we have energy. We have light, we have the air condition, we have anything we want to do with electricity. So this is the basic scheme of the solar cell. Let's see how nanotechnology can help us here. Stop working. Okay. This is one example of nanomaterials in solar cell technology. This concept of solar cell called sensitized solar cell. What we do here, we shine light through this electrode. When we shine light, we have nanoparticles of titanium oxide. Titanium oxide nanoparticles are very common in this type of solar cell. Because what the titanium oxide do, titanium oxide can absorb light and excite electrons to a high level, which then the electrons going into a high level, okay, you have the titanium dioxide, you generate electrons, and then the electrons reduce a dye molecule. Iodide is a dye ion. Why we call it a dye? Because the iodide takes the electron and transforms into another molecule called 3-iodide. I- to I3-. This is a reaction that happens with the electrons that are coming from titanium dioxide. Then what happens? The triiodide goes all the way, it reaches the bottom electron and releases the electron. Just like a car that takes the electrons from here to here. And again, if we do that, we close the circuit. We generate electrons here through light. The electrons go all the way here, and then they go back, and we can have energy, solar energy. Now, where nanotechnology is important here, in the titanium oxide nanoparticles. The titanium oxide nanoparticles are critical in the first step. They take light, excite electrons. Then the electrons can go and reduce the iodide into triiodide, which then go to the other electrode. Now, why people like titanium oxide here? Both because of the energy level, the excitation, but also because they have very high surface area. If you will put just a layer of titanium oxide film, it can still generate electrons, but not enough electrons. If you have many, many nanoparticles of titanium oxide, you can generate many electrons. And then you're going to have an efficient solar cell. So this is called a dye-sensitized solar cell. This technology actually is not so practical for large-scale solar cells. You know which is the material that is most popular in the solar cells that we use now in the field? Silicon. And we're going to see why silicon is so important. But still, this is a very interesting technology, more small scale, and it's a very nice example how nanotechnology can help us. This is just another example, another scheme of the same concept, dye-sensitized solar cell. This one shows you a little bit the energy levels of the system when you excite the electron in titanium oxide to a higher level, which then go to the dye, the mediator that takes the electrons from one side to the other side. Actually, in this case, it's the other way around, but that's okay. Another type of solar cells which uses nanoparticles can be shown here. It's called a nanoparticle heterojunction solar cell. Basically, what we have here, we have nanoparticles that help, conductive nanoparticles, metal nanoparticles like silver, that helps to take the electron from one electrode to the other electrode. So they sit here in the active layer. After shining light, they shuttle the electron, or they help shuttle the electrons or the holes into the other electrode and generating energy. This is just another example of the same concept, calling a heterojunction solar cell, where we have a component, nanoparticles or molecule, that takes the electron, another one that accepts the electron and take it to the other electrode. The most important thing, as we said, we have the electrons going from one electrode to the other electrode. Nanoparticles can be very good in shuttling, carrying the electrons from one electrode to another electrode, which is what we do in solar cell. Now let's talk about the most important these days, the most popular solar cell technology, which is the silicon solar cell. This is the main basic concept of silicon solar cells. There is no nanotechnology here. But first I'd like to explain the concept. Now, what we have here again, we have the electrode that we shine light. This is the main part of the solar cell. And this is the electrode that takes the electrons. Remember, our goal is generate electrons here or induce electron here and get them to the back and close the circuit. Now, why silicon is so good about this concept? Why it's so popular? Silicon is what we call a semiconductor material. The nice thing about semiconductors is that they have relatively narrow energy level. This is a metal. In metal, electrons can move freely in the metal. So metals cannot help us in solar cells, because you connect metal together, electrons will go freely until they're gone. We cannot generate electrons by light. Insulators, the energy level between the energy band gap, the distance between the electronic band and the conduction band, the top band, is very high. So in insulators, it's very hard to take electrons from here and move them here. That's why insulators are insulating. They prevent conductivity. Okay? So if we shine light on an insulator, nothing will happen because the electron cannot go up here and start moving. Semiconductor, on the other hand, are perfect for this job because the distance here between the electron band and the conductive band is relatively close, relatively small distance. And then what we have, when we shine light on the semiconductor, light can give us enough energy to move the electrons from here to here, and then we have generated electrons, generated free electrons. And that's exactly what happened with silicon. Silicon is so good because it's very easy when we shine light to get electrons from the lower band, from the valence band, to the conduction band, and then we can use the electrons. Okay? So when we have a solar cell, a silicon solar cell, we have many silicon atoms. Throughout the cell, we shine light, we shine solar light, and the electrons will jump from the valence band to conduction band of the silicon, and then we can use them. We can take the electrons and we can use them. We can use them for generating energy. Free electrons are energy. So this is why we like and we use silicon as a main material in solar cell. Now, how can nanotechnology help us in this concept? Silicon is semiconductor. The early days of nanotechnology, or the first invention in nanotechnology, were the semiconductor quantum dots. What are semiconductor quantum dots? We can have the same effect of a distance or a good distance between the valence band and the conduction band, not only with silicon atoms, but also with what we call semiconductor quantum dots. There are various semiconductor quantum dots from various materials, because many materials are semiconductors. And people found that when we take very small, nanometer size semiconductor material, they can have the same effect of a small valence band between the low energy and the high energy. So if we take semiconductor quantum dots instead of silicon, we can get the same effect. We can shine light, okay, and we can excite electrons from the lower level to a higher level and get free electrons, which is exactly what we want in solar cells. Now, what is the problem? Silicon is relatively cheap. Where we can find silicon? For example, in the sea sand. There's a lot of sand in the world. So practically, it's easy to make silicon. And this is actually the reason why all solar cells right now are made of silicon. But there are semiconductor quantum dots from various materials that can be made very cheaply and efficiently. And actually, one of the main challenges in this field of semiconductor quantum dots is just developing the technologies to make cheap carbon dots, cheap semiconductor quantum dots. If you make good semiconductor quantum dots, in a cheap way, efficient way, in large quantities, you can compete with silicon solar cells. Let me just show you some examples of semiconductor quantum dots. Okay? In all these cases, there's various configurations of solar cells with quantum dots. Okay? Again, the concept is the same concept. One electrode here that's transparent, another electrode here that takes the electron. You shine light, you have quantum dots, semiconductor quantum dots. They generate electrons because they have low gap. And the electrons will go from here to here, and we're very happy because we have solar cell. Okay? So these are various specific configurations that we use for green solar cells. Now, semiconductor quantum dots are one of the possibilities to make new solar cell technologies. We can actually use the same concept, not with semiconductor quantum dots, but with other materials. Because you know, some of the problem with semiconductor quantum dots is that they can be toxic to produce. You know, some semiconductor quantum dots are made from really bad material, like cadmium. Cadmium sulfide are excellent semiconductor quantum dots. They can generate electrons, you can shine light, and you can move electrons from the low level to the high level extremely efficiently. But cadmium is very bad for you. So you cannot build factories that make cadmium sulfide quantum dots because the cadmium is extremely toxic and you don't want to release it to the environment. So you don't use cadmium sulfide. Another good element for semiconductor quantum dots is arsenic. You know arsenic, Is? Arsenic is a poison. So you can make gallium arsenide quantum dots that will be excellent for solar cells in terms of energy levels. But arsenic is very bad. Nobody wants to deal with arsenic. So this is really one of the biggest problems with semiconductor quantum dots. Silicon is not toxic, is not harmful to the environment. So no problem, we can use silicon. But if we use semiconductor quantum dots, then we have a problem. There are many types of semiconductor quantum dots. Some of them, actually many of them, can be toxic. So that's a problem. And then we have green technologies. Remember our good old friends, carbon dots? We talk a lot about carbon dots in this course. Carbon dots, actually, if you design them correctly, they can do also the same job like semiconductor quantum dots. Because some carbon dots, if you make the surface in a special way, they can also have energy levels that will be good for using sunlight to excite electrons from low level to higher level. And then you have the same effect. And then you have what we call green solar cells. Why green? Because carbon dots are not a problem. They're not toxic. They're made from natural sources, from sugar. for example, or from plants, or from organic waste. So that way you actually solve two problems. You use organic waste to make carbon dots that then can be put in solar cells. Now, it will take time for this technology to be commercial. There are many challenges here of efficiency, of stability, but this is a very promising direction that people pursue for making solar cells. And that's it. Thank you.
Yeah, so thank you, Professor. That was a very nice lecture on the solar energy. So now, any questions for the students first? Okay, I'm having one question.
Sure.
So, what is your comment regarding the stability of quantum dots for the application of solar?
The stability is actually a very important thing because semiconductor quantum dots are fairly stable, quite stable. However, like everything in life, it doesn't last forever. And this is actually the problem of environmental toxicity. Because if you take quantum dots that have bad elements, like cadmium, like arsenic, like gallium, and other elements, over time, they might break and get released to the environment. And this is very bad. This is actually why still semiconductor quantum dots are not very popular in solar cell technology.
But it is comparable with the silicon
In terms of energy, it is, yes.
stability.
In terms of stability, I think it's less stable, yes.
Please go to the next slide, sir. Yeah, here in this green solar energy, you talked about quantum dot, isn't it?
Yeah,
The second figure,
this.
yeah,
This is carbon quantum dot.
carbon quantum dot. And could you put more light on how that those red dots, are they the nitrogen doped?
Yes. The secret of making carbon dots good for solar cells is that you have to tune the energy levels that they will be good for light. So in order to make the levels between the low level and the high level in carbon dots can be tuned. Remember, when we talked about carbon dots, the colors, the different colors of the carbon dot depend on the surface of the carbon dot. So if you put different atoms on the surface, you can change the energy level. And this is the key challenge to make carbon dots good for solar cells. You have to work on the surface, to change the surface, to dope it with nitrogen or sulfur or various different atoms in order to tune the energy.
Thank you.
Any
Very nice. I just made inquiry regarding electrolyte. In this green solar energy, what kind of electrolyte we use?
Very good question. There are many types of electrolytes that people use. Sometimes they are solid electrolyte, sometimes they're liquid electrolyte. Basically, the electrolyte that you use does not depend on the medium that you put here for electron transfer. So some people use ammonium chloride as electrolyte. Some people use sodium chloride as electrolyte. There are various types of electrolytes, which is unrelated to if you use carbon dots or semiconductor quantum dots or silicon atoms.
Sir, nice lecture. Very good. Wonderful. Just might be a stupid question. What is source?
No question is stupid. All questions are good.
What will be the source for nitrogen doping?
It's actually quite easy. Remember the previous lecture when we make the guanidinium carbon dots? If you use a precursor with nitrogen, you'll have nitrogen there on the surface. So you can use amines as your starting material for making carbon dots. Then you're going to have nitrogen on the surface. You can use free nitrogen. It's okay, but it's more difficult because when you start with nitrogen in your reaction, nitrogen is going to sit there covalently attached. If you take external nitrogen, you make carbon dots, let's say, and then you put them in a solution of ammonia, for example, or you bombard them with ammonia vapor, the nitrogen will attach to the surface, but physically. So it's going to be less strong, less stable coupling. So usually when you want to dope carbon dots or put some atoms on the surface, it's better that you put in your reaction the source of these elements, like compounds.
How much is the efficiency of the fluster here?
Again?
Efficiency.
It's quite efficient. To dope with nitrogen is very efficient, actually.
My question is, you told that we can actually tune the energy gap. Like semiconductor, we have very small energy gap, like 1 to 3 milli electron volts. So in quantum dot, how we can control the energy gap by controlling the size?
You mean here?
Here and also other quantum dots we have shown.
Well,
Like quantum dots.
in semiconductor quantum dots, the size determines the energy gap. In the carbon dots, the surface properties determine the band gap. That's the big difference between semiconductor quantum dots and carbon dots.
How certain is effective for the carbon dot? Suppose here in this case.
That's the thing. It's very effective because the mechanism for determining the energy levels is the surface units, the surface residues. That's what happens with the carbon dots. If you have certain atoms, you have different energy levels. That's how you can tune the band gap with carbon dots.
Also, this dots, quantum dots. So what is the medium or like state? Like inside two electrodes, using the material. So how is it solid state? Is it colloidal state or how is it?
Usually you make it in solid state. What people do, they take the carbon dots and they make it in a polymer matrix or in a gel. That keeps them very stable and still allows electrons to go out and go between the two electrodes. So it is basically a solid phase system, which makes the solar cell much more stable.
Any other question?
Just for curiosity, what will happen after using such material for a long period when it is going to dispose in the body? Then it will create the same
Actually, in this system, much less of a problem. Because here, you just have carbon. So you take this, you throw it out, nothing happened. The world is full of carbon. It's not some metal, it's not some semiconductor materials. These are natural carbon atoms. You're right. Nanoparticles can be a problem, but still, most research on carbon dots find that they're not toxic, or they're much less toxic than semiconductor materials, because they're just made of natural sources from carbon. Yeah, no. These devices exist. There are papers of solar cells from carbon dots. They have problems. They're not so efficient as other silicon solar cells, but they're quite good.
How about economic level?
Economic level, they're cheaper because they're just made of carbon, but they don't generate so much electricity yet, and they're not so stable as silicon yet. So these are the challenges that maybe the students here can solve one day, and then we can have good alternatives for silicon.
We can take one or two questions from the students, right? This is direct.
Somebody is interested. Otherwise, we can continue the discussion in the second half of the day. And it's now lunch break. So please join me in thanking Professor Raj for delivering nice lecture. And
This is not good.
We gathered here by 2 o'clock.
I feel that I need to,
Thank you.
so maybe I'll split. If you don't feel